In 2010, a team of researchers mapped a small stretch of seafloor in the Canadian Arctic. Nothing about it seemed unusual. Flat, frozen ground beneath frigid water, the kind of terrain that geologists assume changes over thousands, even tens of thousands of years. 9 years later, they came back to map the exact same stretch of ocean floor again. It was unrecognizable. 41 new holes had appeared, some over 20 meters deep. One of them was large enough to swallow an entire city block. This wasn't supposed to be possible, not on this time scale. Geological change at the bottom of the ocean is supposed to be the slowest, most patient process on the planet, measured in millennia, not in years. And yet, the seafloor had changed dramatically in less than a decade, and when researchers went back again recently, the holes were still growing. Here's the part that should genuinely surprise you. The cause has almost nothing to do with the headline you'd expect. It's not methane explosions. It's not modern climate change. It's something far stranger and far older, the most remote survey site on Earth. The Beaufort Sea sits along the northern coast of Canada and Alaska, inside the Arctic Circle, one of the most remote, least visited stretches of ocean anywhere on the planet. Along the edge of its continental shelf, at depths of around 150 meters, lies a region that scientists at the Monterey Bay Aquarium Research Institute, known as MBARI, have been quietly mapping since 2010. Using autonomous underwater vehicles, robotic submarines capable of mapping the seafloor in extraordinary detail down to a resolution of about 1 meter, the team surveyed a 10-square-mile patch of ocean floor along the edge of the continental slope. At the time, nothing about the site seemed especially remarkable. It was simply chosen because it sat at the edge of what's known as subsea permafrost ground, beneath the seafloor that has remained frozen since the end of the last ice age. In 2019, the team returned to survey the exact same patch of seafloor again. What they found triggered alarm bells across the marine geology community. 41 new sinkholes had appeared in just 9 years. On average, they were about 22 feet deep. The largest was massive enough that researchers described it, almost casually, as big enough to swallow a city block. Published in the Proceedings of the National Academy of Sciences, one of the most respected scientific journals in the world, the study marked the first time researchers had documented this kind of rapid offshore change happening in real time, with hard data, rather than inferring it from older, indirect evidence. Charlie Paul, the senior MBARI scientist who led the research, put it simply, this was the first time anyone had been able to deploy the technology needed to prove that the kind of dramatic landscape change already well known on land in the Arctic was also happening just as fast beneath the ocean, ruling out the obvious suspect. When most people think of giant craters appearing suddenly in frozen ground, they think of one specific cause: explosive blowouts of methane gas trapped for thousands of years beneath the permafrost, suddenly bursting free. This is a real and well-documented phenomenon. In Siberia, on land, more than 100 giant craters have formed this way, caused by buildups of methane gas exploding outward in violent, instantaneous blowouts. It would have been the obvious headline for these new Arctic seafloor holes too. But when the MBARI researchers examined the evidence looking for rock and sediment that would have been violently scattered by an explosion, looking for elevated methane levels in the surrounding water, they found none of it. There was no debris field, no spike in methane, no sign of overpressure that would be required to build toward an explosive blowout in the first place. This wasn't an explosion. It was something slower, quieter, and in its own way, even stranger. Ice that is still forming and still collapsing. The explanation the team arrived at involves a process called thermokarst, essentially. The same kind of ground collapse you'd see when a sinkhole opens up on land above melting ice, except happening here on the ocean floor, above a vast buried layer of permafrost that has been there since the end of the last ice age. Around 11,700 years ago, as Earth emerged from that ice age and glaciers retreated, large sections of formerly exposed, frozen Arctic ground were submerged by rising sea levels. The permafrost didn't disappear, it stayed frozen, buried now beneath the waves, sealed under a few hundred feet of cold seawater. But seawater, even cold seawater, carries a small but persistent flow of heat. Slow-moving groundwater systems, driven by pressure differences far below the seafloor, seafloor have been carrying that heat downward into the buried permafrost for thousands of years, melting pockets of ancient ice, one slow degree at a time. When buried ice melts, it leaves behind a void, and when enough void space accumulates underground, the ground above it eventually has nowhere to go but down. That's a sinkhole. What makes the Beaufort Sea site so unusual isn't the process itself, it's the speed. Researchers found that ice is actively forming in some areas of this seafloor and decomposing in others, sometimes only meters apart, creating what the lead researcher called a dynamic, constantly shifting underwater landscape, completely unlike the static seafloor terrain that most ocean maps assume exists. And critically, this isn't a story about modern, human-driven climate change. It's a story about a thaw that has been quietly unfolding since the literal end of the Ice Age, only now becoming visible because we finally built the technology capable of watching it happen. This isn't an isolated case. The Beaufort Sea sinkholes are part of a much larger pattern of strange transformation happening across the Arctic seafloor, and not all of it is as gentle as slow collapsing ice. In the Barents Sea, north of Norway and Russia, scientists have documented more than 100 enormous craters, some over a kilometer wide, carved into the seafloor by genuinely explosive methane blowouts that occurred roughly 12,000 years ago. Also, at the end of the last ice age, these ancient craters are not just historical curiosities. Recent research has found that many of them are still actively leaking methane into the ocean today, more than 10,000 years after they first formed. A study using advanced three-dimensional seismic imaging, capable of seeing deep beneath the seafloor into the solid bedrock below, found something unexpected underneath these Barents Sea craters. Long-standing structural weaknesses in the rock itself, fault lines that have existed for far longer than the Ice Age thaw that triggered the original eruptions. In other words, the craters weren't random. They formed exactly where the bedrock was already weak, where ancient fractures gave trapped gas and meltwater an escape route to the surface. This matters because it means the Arctic seafloor isn't just one uniform layer of frozen ground slowly thawing from above. It's a complex, ancient structure, riddled with old weaknesses, responding to heat and pressure in ways that scientists are still mapping for the first time. And as more of the Arctic seafloor gets surveyed using the kind of high-resolution technology MBARI used in the Beaufort Sea, researchers are finding that this kind of rapid, hidden transformation may be far more widespread than anyone previously assumed. Recently discovered, Greenland's giant pockmarks. Just in the last couple of years, scientists conducting seafloor surveys off the West Greenland shelf identified an entirely new field of what researchers call giant pockmarks, crater-like depressions, similar in character to those found elsewhere in the Arctic, but in a location that had never been closely studied before. Every new survey seems to reveal more of the same story. The Arctic seafloor, once assumed to be among the most stable, unchanging environments on the planet, is turning out to be one of the most quietly dynamic, an ocean floor that won't stay still. It's worth pausing on why scientists consider this discovery so significant beyond simply being a strange and slightly unsettling fact about the Arctic. As Arctic sea ice continues to retreat, human activity in the region is increasing. Shipping routes through the Arctic are opening up that were previously impassable for most of the year. Oil and gas exploration has expanded along sections of the Beaufort Sea shelf. Underwater pipelines and communication cables are being planned and laid across seafloor terrain that, until very recently, almost everyone assumed was geologically stable. Charlie Paul and his colleagues were direct about the implications of their findings. Seafloor changes on this scale and at this speed carry serious consequences for any infrastructure built on or near it. A pipeline, a cable, a drilling platform, all of these are typically engineered with the assumption that the ground beneath them will remain essentially fixed for decades. The Beaufort Sea data suggests that, at least in some Arctic locations, that assumption may simply be wrong. There's also a climate dimension here, though one the researchers are careful to keep separate from the cause of the sinkholes themselves. Permafrost, both on land and under the sea, stores enormous quantities of ancient organic carbon. As it thaws, by whatever mechanism, that carbon has the potential to be released, primarily as methane, one of the most potent greenhouse gases. The Barents Sea craters are a sobering reminder of just how long that process can continue. Methane has been leaking from craters that formed 12,000 years ago, and it's still leaking today. Whatever begins thawing beneath the Arctic seafloor doesn't necessarily stop on a human timescale. It can keep going for millennia. Go back to that first survey in 2010. If you had stood at the edge of that patch of Arctic seafloor and looked out across it, you would have seen nothing unusual. Flat ground, dark water, a landscape that, by every assumption geology had made for over a century, should not have changed in any visible way within a single human lifetime. 9 years later, 41 craters had opened beneath the waves, not from an explosion, not from anything sudden or dramatic happening today, from heat that began moving through the ground at the literal end of the last ice age, 11,700 years ago, and has simply never stopped. There's something quietly humbling in that. We tend to think of the ocean floor as the most unchanging place on Earth, the one part of the planet that geological time has sealed away from us, untouched, ancient. Still, the Beaufort Sea tells a different story. Beneath the waves, the ground is still settling the accounts of an ice age that ended before written history began. And as we build more pipelines, more cables, more platforms across the Arctic seafloor, the ground we're building on is, quite literally, still finding new ways to give way.